Confidential Pre-Patent Technical Disclosure Integrated Plasma Reformer Diesel Efficiency and Emissions Treatment System. With vortex cooling, thermoelectric recovery, and exhaust plasma filtration. This document contains proprietary technical concepts. Disclosure to third parties without written consent of Patrick W. SEELY is prohibited. 1. Abstract. This disclosure describes a novel integrated system for diesel internal combustion engines comprising 3 primary subsystems operating in a closed thermodynamic and electrochemical loop. A plasma fuel reformer that cracks long-chain diesel hydrocarbons into shorter, more reactive species prior to injection. A Reinke-Hilsch vortex tube cooling stage that densifies and quenches the reformed fuel vapor, preserving reactive radical species and improving injector atomization. A high-voltage wire mesh exhaust plasma reactor that destroys NOx, captures particulate matter, and oxidizes unburned hydrocarbons, powered substantially by thermoelectric generators harvesting waste exhaust heat. The system is designed to operate within the energy budget of a standard diesel powertrain by recovering waste heat via TEG arrays to power both plasma stages, thereby achieving net thermal efficiency improvements estimated at 9 to 20%, with emissions reductions projected to meet or exceed Euro 7 and EPA Tier 4 standards without conventional DPF, SCR, or EGR systems. 2. Field of the invention. This invention relates to internal combustion engine technology, specifically to plasma-assisted fuel reforming, thermoelectric energy recovery, and non-thermal plasma exhaust after treatment applied to compression ignition engines in an integrated, self-powered closed-loop configuration. 3. Background and prior art. 3.1 Limitations of conventional diesel systems. Modern diesel engines face 4 persistent engineering challenges. Incomplete combustion of long-chain hydrocarbon fuels under transient load conditions, producing particulate matter and unburned hydrocarbons. High NOx emissions resulting from peak combustion temperatures, requiring external aftertreatment that reduces efficiency and adds cost. DPF systems that create exhaust back pressure, reducing thermal efficiency by 3 to 7%. Large quantities of waste heat rejected through the exhaust stream, typically 30 to 40% of fuel energy, that are substantially unrecovered in conventional designs. 3.2 Existing technologies addressed. No prior art is known to the inventor combining plasma fuel reforming, vortex tube fuel conditioning, and TEG-powered exhaust plasma treatment in a single integrated closed-loop system as described herein. 4. Summary of the invention. The invention provides a bolt-on or OEM integrated diesel engine subsystem consisting of 3 electrochemical and thermodynamic stages connected in series with the engine's fuel delivery and exhaust systems. Stage 1, Plasma Fuel Reformer, a non-thermal plasma reactor through which atomized diesel fuel vapor passes prior to injection. The plasma field cracks C10C15 hydrocarbon chains into C2C8 fragments and generates free radical species that survive within the fuel vapor matrix. Stage 2, Vortex Tube Fuel Conditioner. A Reinke-Hilsch vortex tube driven by turbocharger outlet pressure that cools the reformed fuel vapor, increasing density, quenching radical recombination, and producing a biphase fuel mist with superior atomization characteristics. Stage 3, Exhaust Plasma Mesh Reactor. A high-voltage twisted wire mesh positioned in the exhaust stream downstream of the turbocharger that destroys NOx via electron dissociation, captures particulate matter electrostatically, and oxidizes residual hydrocarbons. Powered by a TEG array harvesting exhaust thermal energy. 5. Detailed Technical Description. 5.1 System Architecture Overview. The complete system energy and material flow is represented as follows. Confidential Pre-Patent Technical Disclosure SEELY Plasma Reformer Diesel System. 5.2 5.2 Stage 1, Non-Thermal Plasma Fuel Reformer. 5.2.1 Operating Principle. Diesel fuel is atomized and passed through a non-thermal plasma discharge zone. NTP operates at near ambient gas temperature while generating high-energy electrons that dissociate molecular bonds without bulk thermal heating of the fuel mass. Primary reactions within the plasma zone. 5.3 Stage 2. Reinke-Hilsch Vortex Tube Fuel Conditioner. 5.3.1 Operating Principle. The Reinke-Hilsch Vortex Tube is a passive thermodynamic device with no moving parts. Compressed gas is injected tangentially into a cylindrical chamber, creating a high-speed vortex. Angular momentum transfer between the outer and inner vortex streams produces a temperature separation. The cold stream exits one end, the hot stream the other. The reformed fuel vapor from stage 1 is passed through the cold stream, achieving the following effects. Cooling of reformed vapor by 30 to 60 degrees Celsius, increasing fuel density and mass per injection event. Quenching of radical recombination, lower temperature significantly extends the lifetime of H and O species. Partial condensation of heavier C9 plus residual fractions into fine liquid droplets, creating a biphase aerosol with superior atomization characteristics. Natural fractionation, lighter, more reactive species remain in vapor phase while heavier fractions condense, effectively enriching the vapor phase with the most combustion beneficial species. 5.3.2 Vortex Tube Specifications. 5.4 Stage 3, Exhaust Plasma Mesh Reactor. Stage 3, Exhaust Plasma Mesh Reactor. 5.4.1 Operating Principle. A high-voltage twisted wire mesh is positioned in the exhaust stream downstream of the turbocharger. Operating as a non-thermal plasma reactor, the mesh creates a corona discharge zone through which exhaust gases pass continuously. The charged gas species and high-energy electrons drive several simultaneous reactions. 5.5 Thermoelectric Generator Power Recovery Array. 5. Five point 5.1 Purpose. The TEG array is the key enabler of system energy closure. By harvesting waste heat from the exhaust stream, it generates sufficient electrical power to operate both plasma stages with minimal or zero net parasitic draw from the engine's alternator. 6. System energy budget and efficiency analysis. System energy budget and efficiency analysis. 6.1 Power budget. 6.2 Thermal efficiency gains. 7. Prototype engineering specifications. 7.1 Prototype objectives. Validate. 7.3 Prototype build phases. 8. Proposed patent claims. The following represent preliminary claim concepts for formal patent drafting by a registered patent attorney. 8.1 Independent claims. Claim 1, System claim. A diesel engine fuel treatment and exhaust after treatment system comprising a non-thermal plasma fuel reforming reactor positioned in line between the fuel supply and fuel injectors. A Reinke-Hilsch vortex tube positioned to receive reformed fuel vapor from in-cool said vapor using turbocharger-sourced compressed gas. And a high-voltage wire mesh plasma reactor positioned in the exhaust stream downstream of the turbocharger, wherein electrical power for and is supplied substantially by thermoelectric generators harvesting thermal energy from the exhaust stream. Claim 2, Method claim. A method of improving diesel combustion efficiency and reducing exhaust emissions comprising the steps of cracking diesel fuel hydrocarbons using non-thermal plasma prior to injection, cooling and densifying the resulting reformed fuel vapor using a vortex tube, injecting the conditioned fuel into the combustion chamber, and treating exhaust gases with a high-voltage plasma mesh to destroy NOx and capture particulate matter, wherein energy for said plasma stages is recovered from exhaust waste heat via thermoelectric generation. Claim 3, Energy Recovery Claim. The system of Claim 1, wherein thermoelectric generators are arranged in a modular array in thermal contact with the exhaust conduit, providing sufficient electrical output to operate both plasma stages with zero or near zero net parasitic draw from the engine crankshaft. 8.2 Dependent Claim Concepts. Vortex tube cold stream directed to reformed fuel. Hot stream directed to preheat plasma reactor. Plasma reactor electrode material comprising tungsten iridium alloy with automated reverse polarity self-cleaning cycle. Exhaust plasma mesh comprising Inconel or platinum-coated wire mesh with pulsed DC discharge. System further comprising elimination of diesel particulate filter and selective catalytic reduction system. AQ integration for load tracking plasma power modulation, biphase fuel aerosol formation by controlled condensation in vortex tube cold stream. 9. Known technical risks and mitigations. 10. Statement of novelty. To the best of the inventor's knowledge, the specific combination of non-thermal plasma diesel fuel reforming, Rinke-Hilsch vortex tube conditioning of plasma reformed diesel vapor, TEG-powered exhaust non-thermal plasma treatment, closed energy loop in which exhaust waste heat powers both plasma stages, elimination of DPF, SCR, and EGR through plasma-based substitutes. As an integrated system applied to a diesel internal combustion engine has not been described in any prior patent, academic publication, or commercial product known to the inventor as of the date of this disclosure. Individual component technologies are known in isolation. The novelty of this invention resides in their integration into a closed-loop, self-powered, cooperating system. 11. Inventor Declaration and Signatures. I, Patrick W. SEELY, hereby declare that I am the sole inventor of the subject matter described in this technical disclosure. That this document accurately represents the invention as conceived, and that I am prepared to assign rights and cooperate fully with Patent Counsel in the preparation and prosecution of patent applications based upon this disclosure. Document reference: PWS 2026001 Diesel Plasma. This document was prepared for peer review purposes. It does not constitute a filed patent application. Formal patent filing should be conducted by a registered patent attorney or agent.